Hello friends, my name is Tushar Roy. Just kidding. Hi guys. So I'm going to be looking over the problem set matrix zeros, which is number 73 on Leetcode, and I'm going to be trying to explain the best space and time complexity for this problem, as well as going through the thought process behind it. Now keep in mind, the main lesson you should take away from this isn't how to solve the problem, but the thought process that goes into finding the best solution and what kind of makes sense as an approach and pushing the boundaries to make sure that approach kind of gets through. Or if it can't get through, what are the barriers stopping it? So the problem is given an m by n matrix, if an element is 0, take all of the elements in that row and all the elements in that column and replace it with 0. Now we can't just do that, for example, at the same time, because then we would set this whole row to 0 and all of the columns become 0 and the whole matrix becomes 0. So what it's actually asking is, can we replace all the zeros in our original matrix such that they'd all become 0 after one iteration? And in order to do this the trivial way, we're going to look at what if we do a second matrix, a dummy matrix, only make the changes in that, and then transfer all of our changes back to the original matrix so that we have the one iteration occurrence. So I'm going to post some code for the example, and hopefully that helps you see what I'm talking about. And so here's our code. We have an m by n matrix, which we throw out right off the bat. We make a dummy matrix, which is the same size, and then we do a little loop to populate the dummy matrix so that it's the same as the original matrix. Now we iterate on a 2D loop, and if we see 0 in the matrix, we take all of the elements in that matrix and we set it to 0, and all of the elements in that matrix in the column as well as the row, and set that to 0 as well. And then we go back to the original matrix because we're only updating the dummy matrix before to avoid any collision problems, and then we're changing it back and we have a working solution. Now, there's a few problems with this solution. Not that it doesn't work, but it's very slow. And although it may not seem slow, we're going to look at some little sketch of why it's slow. So let's say we write down the exact premise of the example. The basic example is just a bunch of ones surrounding a 0. In this problem, it's not so bad. We're just making this row 0 and this column 0. But let's take the example of having a second 0. It looks like there's no problem. It's m times n. However, while we only update this row once and this row once, we're updating this one twice. And twice isn't so bad, but let's think about the worst case. A matrix full of zeros. Very scary. Now, what's the problem with this? Well, let's consider this is m and this is n. Every time we want to update it, this is m and this is n. There's m plus n updates. And how many times are we doing that? We're doing it for this thing, we're doing it for this thing, we're doing it for this thing. And that means we're doing it m times n times. And so this is the time complexity. It's O of mn times m plus n. And that's pretty bad. I mean, we were aiming for O of m times n time complexity, but we didn't get it. And the reason for that is redundancy. We want to be able to make sure that we only check each row and each column once, and then we update it that way. Now, let's try doing it. So I'm going to propose a solution. What if we're only updating based on row and column by having an array for each element in the row and each element in the column? And if we set that boolean to true, then after the fact, after we loop through all the elements in the original matrix, then we go through every row that was marked and set that to 0, and every column is marked and set it to 0. Now I'm going to post some code for this second solution and show you what it looks like. Now we have row and column matrix, and we iterate, and if we see a 0, we set that row and column respectively to true, and then we go through all of the rows and columns and set them to 0. Now hopefully that makes sense. What we're essentially doing is, given the same sort of problem, we're saying, look at this matrix. This row has to be 0, and this column has to be 0. And if we know that's the case, then we only have to update them once. And the time complexity is O of m times n, because the first time we're only checking each element at least once. And then when we're updating, we only have to update each element at most twice, because it could be a row and a column, but it's still O of m times n time. And now the space even got reduced. Now we have O of m plus n space, and the reason for this is because we're making 2 Boolean arrays. One of them is of size m, one of them is of size n for rows and columns, and that's all we need. Now, this is a pretty good solution, but how do we know if it's optimal? Well, we know that the time is optimal because O of m times n is the smallest we can get. We have to check each element in the array at least once, and that means we're going to make O of m times n checks no matter what. We can't get any better than this. Maybe we could do less checks, but ultimately this is fine. However, space could be better. Now, there's only a few cases. Either it's O of m times n space, where we make a new dummy matrix. We make a set of row and column arrays, which is m plus n, which is our current solution. And then the best case is O of 1 space. Now, what stops us from being O of 1? Well, we would have to update all the information in the original array and only use constant flags. Now, is this possible? The answer is yes, but it's not exactly trivial how to do it. Now, let's go back and see what we could do. Well, right now, we see that given this matrix, we would need to have some place in it to store whether or not we should change them in the end. And we can do this by noticing that the rows and the columns in the first rank are all that we need. So if we were to say, when we see this 0, mark this as 0, mark this as 0, as if it was our current solution, then we would have no added space. Now, I'll show you what that code looks like. For the third time, this is our third iteration of code. And we're just making slight improvements on the previous time. Now, we have some really clean code where we set the edges to 0 whenever we see them, and then we go through the edges and say, if the edge is 0, we populate that row, and we populate the column. And all is well, except let's go to example 2. Now, what's the problem here? Well, as we notice, this edge 1 is already 0, and this already assigns a red flag for us. This is 0, so that means we're going to mark this as 0 and this is 0. And then when we do this code, where we're zeroing out the row or the column, no matter which way we do it, if we mark this as 0 first or this is 0 first, we populate one of them, and then when we're going to check all of these, they're already all going to be zeros. And then this whole matrix will become zeros if that's the case. Now, we don't want that. We're essentially losing data that we can't preserve because we're making the matrix our dummy arrays for booleans, and we're not doing anything to safeguard ourselves from that. But we actually can do something to safeguard. I'm going to propose a final code and a final solution that works with this method. Now, we have a boolean for rows and a boolean for columns. Now, what does this mean? Well, if we actually look at the edges and we see a 0 on the edge, then instead of changing the matrix to 0 over there, we make a special case and set the boolean for row or column to 0. Then when we iterate from 1, where we iterate just from everything besides the edges, set the zeros accordingly as our same solution from before, and then we separately do row and column, just to get over this little problem we had before. And because we're only having 2 additional booleans, it's still constant space, and we're only updating the original matrix outside of those 2 booleans. So now if we go back, we can actually definitively say that since the time didn't change, it's still O of m n time from our previous solution. However, now it's O of 1 space. We can say this is an optimal solution without a doubt in our minds. Why? The same logic holds for O of m times n time. We didn't make it any worse, There's no faster way to do it than this because we have to check every element at least once. And all of one space for any solution is the fastest because it's already constant. We can't do anything better than that. But for that reason, we found an optimal solution. I hope you guys liked this explanation. Good luck on your interviews, and I'll talk to you again.